Hello and welcome to video 22 of the How to Make a Game Like Minecraft in Unity series, and in this video we are going to be tackling fast clouds. So I was going to try and do the whole cloud system in one video, but then the whole reason that I'm doing the cloud video now rather than the cross-trunk lighting video is because the cross-trunk lighting video is going to be a bit of a monster, and I didn't think I had time to do a stupidly long video because as long as the video itself is to watch, it's so much longer to make. So I thought I'd do the cloud one instead, which ended up being at least 5 times longer than I thought it would, and that's just to do the fast clouds part. So let's get straight into it. The first thing we're going to do is we're going to run the game and just change these settings because we left them on some random settings before. We want enable threading and we don't want animations, and I'm going to leave the view distance quite low because we don't have to wait for the world to load up every time we're testing it. And then just click done, and that has saved our settings. And then we're going to go into our scenes folder and we're going to rename this main here because we've got main menu, that's this one. We're going to rename this to world, or you can call it game or something, just something descriptive. And then we're going to open that because we don't want to be going through the menu every time we want to test out what we're doing. So if we go into our scripts and we find our voxel data script and open that up, we're just going to add a little value that will come in handy later in this video. I'll just stick it here, and it's just going to be to get the center of the world. So better remember, the center of the world will change depending on the world size. And we'll just do that by returning world size in chunks times chunk width, and then we're dividing that by 2. And that's as simple as that. And seeing as we've created this, we may as well go into our world script and use it in this point down. Is it spawn position? Yeah, I think spawn position, where we create the spawn position. There's no point in doing all this here when we've got a value ready for it. So we just replace all this with voxel data dot world center. If we go back into Unity and go into our textures folder, we can see that I have brought in this texture here. Now, we could do this with noise, with purling noise. However, that's not the way Minecraft does it, as far as I can tell. And also, that would mean going over some stuff that we've already done. And as much as possible, I'm trying to do things, without making it unnecessarily complicated or difficult. I'm trying to do things in different ways so that we're not just repeating ourselves, so that we're doing something a bit different every time. So we're going to use the same way that I think Minecraft do it, which is to use a repeatable tiled texture to determine when the clouds are. So this is one that I found on the internet. I couldn't find anyone to credit with this one. I think it might be from the actual game though, which would explain why. But yeah, so this is just a bog standard noise texture, and we just need to do a bit of setting up. So first off, we need to tell it that alpha is transparent. We need to enable read write, and we may as well set this to 512 because the size of the image is 512. But also it's important to note that if your texture is not a multiple of 2, the way that we're going to do it will not work. So it has to be 32 by 32, 64 by 64, 256 by 256, 4096 by 4096, whatever it is, it has to be a multiple of 2, or a power of 2, I think it is, sorry. Or the way that we're going to do it will not work. So apply all that, and then let's go into our scripts and create a cloud script. We're just going to call it clouds. Let's open that up. So the first thing we're going to create is a public int, which we're going to call cloud height. I'm going to set it to 115. Obviously in Minecraft it's different. I think it started out, it was 2 blocks above the maximum, so it should be 100, what we've got, 120, it should be like 130 or something. But then the size of the chunks was extended to 256, and that made the clouds just above halfway in the total build height. We haven't done the double height build height yet, so we're still on 128 high chunks. So we're just going to put this at 115 so that it is with, well actually we'll make it a bit lower. We'll put it at 100 so that it is within the build height, and we're going to create a reference for the aforementioned texture, which we will make private because we don't need to get it anywhere else. Texture 2D, and we're just going to call it cloud pattern. And we don't need to, but it's better if we set it to null, because whenever you set something as serialized field and you don't give it a value, it says that it comes up with a warning. This value is never assigned. So if we set it to null, it just stops it throwing up those annoying warnings. We're going to create a bool array, a 2-dimensional array, and this is going to work very similar to the voxel map in our chunk scripts. And we're going to call it cloud data. Now, as you will probably recognize from many of my other videos, we're going to need some lists to store our mesh information. So a list of vertices, which are vector 3s. A list of ints, which are triangles, or a list of triangles which are ints. And we're going to give ourselves a list of normals, which are also vector 3s. We don't need any UVs for this one because we're not going to be texturing our clouds, we're just going to be giving them a solid color. And also we need an int to keep track of how many vertices we have put into our lists. We need a start function. And in our start function, we're going to say transform.position equals new vector 3, and we're going to get our voxel data.world center. We're going to put it at cloud height, and obviously voxel data.world center again. Mesh filter, which we're just going to call MF for now, is going to equal get component mesh filter. And then just so we don't forget, we'll go back into Unity now. We will create a cloud object, create empty, we'll call it clouds, and we're going to add our cloud script there. And let's drag these values in before we forget. So our cloud texture there, and we want to add a mesh renderer, because you can't see it without a renderer, and a mesh filter, which is what we need to modify. So now we're not going to forget to do that. Now we need to create a mesh to put on that mesh filter. So first off, we're going to say private void void load cloud data. We don't need to take in any values for this, and this is going to populate this array. Before we do that, actually, we're just going to create another int, which we're going to call cloud text width. So that's just the width of the cloud texture, and then we'll set that in here. Cloud text width equals cloud pattern dot width. So cloud data equals new bool, and we'll just say cloud text width by cloud text width. Now we're going to need an array of colors for our texture. Now we could just use getPixel on the texture. There's a function called getPixel where you give it the coordinates of a pixel and it returns that pixel, or it returns a color representing that pixel. We could just use that. However, that is quite slow compared to using getPixels, which returns an array of colors, and then we can manipulate that array. So that way works out quite a bit quicker than if we just individually grab pixels from the texture directly. So first of all, let's initialize our array. So color, it's a one-dimensional array, which is a bit annoying, but that's the way they do it. And we'll just call it cloud text, and it's going to equal cloud pattern dot get pixels. So now we're going to loop through the color array and set all of our bools. We'll just copy that because I'm not sure how good this is going to look after editing, but my typing today is absolutely atrocious. So there will be as much copying and pasting as possible. So this is going to be looping through all of the positions in the texture. However, this is a one-dimensional array, so we can't simply use X and Y like we will be doing in this two-dimensional array. So the way we get around that is, first of all, we set it X and Y. And then we're going to say equals, because it's a bool, we need to give it a true or false value. We're going to get our true or false value by passing in a condition directly, rather than saying if this, then that, or whatever. We're just going to give it the condition directly. And we do that by putting a conditional statement in some brackets. So cloud text, I'm sorry if you can hear noise in the background, but there's a guinea pig in the room with me and it seems to be going absolutely mental right now. Cloud text, and then we get the position by saying y times cloud text width. So that's getting us the up and down position on our texture. The cloud text width times the y value plus x, and then that gives us the position along. And then we want the alpha value, and we're going to say if that alpha value is greater than naught. Sorry, this should be cloud data. So what this is doing is, if this condition is true, it's setting it to true. If it's false, it's setting it to false. And all we're doing is we're looking at the opacity value of that particular color. So all we're saying is the opacity greater than 0? If it is, then there is cloud there. And if it isn't, there isn't cloud there. So next we need a function to get a mesh out of all this. So let's say mesh get cloud mesh. Again, we don't need to take any values for this. And we'll just, once again, copy this because Lord knows I can't type it. And we're going to be going to cloud text width once again. And this time, what we're going to do is say if cloud data xy. So that's if that is true, because that's storing a bool, so it's a condition in and of itself. If it's true, then do this. And what we're going to do here is we're going to call a function that we haven't created yet. Just pass in the x and y value. And then at the end of the function, now this function, when we've written it, is going to automatically add to these lists. So once we've done that, we're going to say mesh equals new mesh. Mesh.vertices equals vertices.toArray. Mesh.triangles equals triangles.toArray. Mesh.normals equals normals.toArray. And then we're going to return mesh. So now to get rid of this error, we just need to create that function. So let's go down here and do that. We're going to do another private void, add cloud mesh data. And this time we do need to take in some values. We need an int x and an int z, I'm going to call it. So add for vertices for cloud face. And we're just going to add a new vector 3, and it's going to be x0 x z. Now these are local position values. So the global position, the position of where this actual piece of vertices will be in the world, or this piece of mesh will be in the world, will be determined by the object that it is on. However, this here is a local value to this game object, which is why we're not giving it a y value, because we're already setting our y value up here with the cloud height. So if we also put cloud height here, then the game object would be what did we set it at, 100? The game object would be at 100, and then the mesh would be 100 above that. Now if we just copy these, because we need to add 4 of these to represent one cubic face, one square, one quad, whatever you want to call it. And then we're just going to go around. So we're going to go bottom left corner, top right corner, bottom right corner. So that is x and z, and then x and z plus 1, and then x plus 1 and z plus 1, and then finally x plus 1. Now for the normals, we know what direction our faces are facing, so we can just add them directly. And just because I don't want to type out 4 lines of code when I can type out 2, we're just going to say for int I equals 0, I is less than 4, I plus plus, normals dot add vector 3 dot down. Just remember the cloud, we're going to be looking up at the clouds. We'll handle looking down at the clouds in the fancy clouds video, because as far as I know, it's not an issue in fast clouds. I don't think you can see fast clouds from above. Could be wrong about that. Either way, we will be fixing it in the fancy clouds video. So there are 2 triangles to a quad, so let's add the first triangle. And we're going to do this the manual way, so triangles.add vert count. Now, this is sort of counterintuitive. We need to go backwards, anti-clockwise, because we're going to be looking at these from underneath. So we want the bottom face, not the top face, to show up. So I've worked this out in advance, so trust me, this is the right way around. But this is basically drawing the triangles anti-clockwise. So we're starting off with the second one. That's this one. What would that be? The front left vertices. And then I'll just copy this. And then the next one is the bottom left vertices, and then the final one is the front right vertices. It's a bit difficult to visualize, really. It's a lot easier to think of it as up, down, left, right. And then we're going to add the second triangle. And the order this time is 2, 0, 3. And then we want to increment our vert count. And we just do that by saying plus equals 4 because we've added 4 vertices. Now if we go back up to our start function, we can say load cloud data and then mf.mesh equals get cloud mesh. Now we can try this, and it's not going to work for a reason I will show you. So the first thing you'll notice is that it's purple, which for those of you who've played with Unity before in any depth will probably know why. We haven't given it a material to make it not purple, which we'll handle that. In fact, we'll just do it now straight away. So if we just go into our materials folder, create a new material, there we go. We'll call it clouds, and then we'll just make it unlit for now. Unlit color. And we'll set the color slightly off white. And then we can drag that onto our clouds component. There we go, at least the white now. However, we gave it a square texture, and that is not square. You don't need to be an expert in geometry to know that. That's a rectangle. So the reason for that is if we go into our clouds object here and we find our mesh, which is here, and we click on this, you can see there are 235,880 verts. Now Unity doesn't do that many verts, or at least it does. We could change the type of mesh to accommodate more verts. However, that's not really going to benefit us in the long run because, as you'll see later on in the video, we really need our clouds to be broken up into smaller chunks anyway. So rather than increase the memory footprint of the mesh and make it allow more verts, we're going to break it up into smaller pieces. So firstly, let's go up to here, and we're going to need a public reference or a serialized field reference to our material. And again, we're going to set it to null so we don't get an annoying error or warning, and then we're immediately going to go in and drag it in so we don't forget to do it later, because that is something I do on a regular basis. So we'll just put that in there. We can get rid of this mesh renderer and mesh filter because we're not going to be using that anymore. What we are going to do is we're going to create a function to make a whole game object. So private game object, create cloud tile. It's going to take in a mesh and it's going to take in a position. So we're going to say game object new cloud tile equals new game object, and then we're going to say new cloud tile dot transform dot position equals position, new cloud tile dot transform dot parent equals transform. So that just makes things nice and neat in the hierarchy. It's going to put it as a child of this clouds object, and then just so we can see what's going on in the hierarchy, we're going to give it a name as well. So new cloud tile.name equals, and then we're going to say cloud space plus position.x plus comma and a space in speech marks just to make it neat, position.z. Remember, we're not using the y position because they're all on the same level. And then finally, well, not finally, there's a few more lines yet, mesh filter mf equals new cloud tile dot add component, and then mesh renderer mr equals new cloud tile dot add component mesh renderer. And then down here we can say mr dot material equals, and then we're just going to grab that cloud material, and then mf dot mesh equals mesh, the mesh that we're going to pass in, and then we can just return new cloud tile. So that creates a whole game object with mesh renderer and mesh filter from scratch. So we're going to need a couple of other values before we carry on. One of them we're going to call cloud tile size. So cloud tile size, and that is going to be the size of our individual cloud pieces that we're going to break our larger tile into. And then we're going to need a vector3 int, which we're going to call offset, and then we'll set those values. So cloud tile size, and this is why our texture needs to be a power of 2, because we're going to set our cloud tile size to the same size as our chunks. So voxel data dot chunk width. And the reason for that is because it makes it a bit easier to tie this into the check view distance or the player movement updates that we've already got in place. So later on when we have the clouds follow the player around, because obviously if there's just a 512 by 512 grid of clouds in the middle of the world and it just stays there, it's not going to be very good looking. So we need those clouds to follow the player around, but also they need to look like they're fixed in the world, so we can't just have the position of the clouds follow the player. We need to actually move the clouds while keeping the clouds in the same physical space. I'm making a mess of explaining this, but basically if we tie the width of the cloud tiles in with the width of the chunks, then that means that we can use the same update system. And then offset is going to be spelt right, is going to equal a new vector3 int, and we're going to say minus cloud data dot, no, we're not going to say cloud data dot get length because we have a value for that. So minus cloud text width 0 because we're not doing anything with the height, minus cloud text width. So we'll go back down to here, we're going to add another function. So now to start tearing up what we created in the earlier part of the video. So if we grab these, no, not that one, these 4 values here, just rip them out. We're going to plonk them down in our, where is it, here. And then we're going to enclose all of this in a for statement and a couple of if statements, or a couple of for statements and one if statement. So we'll say for int x increment equals 0. And the reason we're going to be keeping this x and z, so that's why we can't say just x. X increment is less than cloud tile size, x increment plus plus. And then we'll copy that and do the same with z. And if we just go down here and enclose those. This error we get in here is because we need to set this to 0. We need to give it a value before we can use it. And then the next thing we're going to do is we're going to create 2 values, which we're going to say int x val equals x plus x increment. And then same for z. Z val equals z plus, don't know where that equals sign came from, z plus z increment. And then we're going to, the whole purpose of this is because what we're going to be doing now is this x and z value is going to be sort of the position of the cloud tile. So like the bottom left hand corner or the back left hand corner of the cloud tile. And then the x increment is going to be each position within the cloud tile map. I'm doing a really terrible job of explaining this. So if I'll just pull this picture up, it might make it a bit easier to explain. So we're breaking this up into chunks of 16. And what we're doing is x and z value represents the bottom left hand corner of each chunk. So this is a rather large chunk, but if we were looking at a chunk, then this down here would be the coordinate we're passing in. And then the x increment and the z increment represents each point within this chunk. So that's why we need this x val, because this x val gives us the actual position, which corresponds to, where is it, cloud data, which is what we use to check if there is a cloud at a given point. So we're going to say if cloud data x val z val, and then once again wrap all this up in those curly brackets. And then we just need to change these because we need to use the x increment value, not the x value, because the x value is going to be the same for all of this, but the x increment value would change. Now we're going to change this to a mesh instead of a void, and we're going to change the name to create cloud mesh. And we're going to steal this code and plonk that in the bottom here. Now if we turn our attention back up to this where we've got all these errors, and we're going to simply, well, first off, we're going to just call it create clouds, because whatever we called it a second ago is no longer accurate. And we're going to make it a void because it's no longer returning a mesh. And we're going to delete this. Now we're going to say create cloud tile. And then to get the mesh, we're going to say create cloud mesh, pass in our x and y values. And then for our position, we're going to say new vector3 x0 z y, sorry, plus transform.position. So that offsets it by wherever we've put our cloud position, and then we're gonna add that to our offset value. Now if we go up to our start, we don't need this mesh filter part anymore, and we don't need to directly set a mesh anymore. We need to carry on calling our load cloud data. That function hasn't changed, but now we call our create clouds function. And if we run that, we should find we have an error. Oh, I know what I've done. So in this loop here, this should be plus equals cloud tile size, because we're not adding one every block, we're adding one every cloud tile. Let's just try running that again. There we go. Now we've got the full size 512 by 512 cloud texture tile map thing. However, it's starting at 0, and that is because this needs to be divided by 2 and enclosed in brackets. So now we've finished fixing all those errors. Let's try that. Okay, there we go. Right, we've got some clouds. So obviously, as I was saying before, there's no use to these clouds if they don't move with the player, because if I just grab our player here, and this is gonna completely break the chunk loading algorithm because it's not designed to work this fast, but if I grab the player and just drag him over here, as you can see, the clouds are soon left behind. Our player's stuck in the ground. Yeah, so we've left our clouds behind. Oh, we're in a tree. So that's no good. So let's get that working. To do this, we're going to create a dictionary, which I think might be the first time I've used a dictionary in any of my videos. So our key is going to be vector2 int, and the type is going to be game object. So for those of you who haven't played with a dictionary before, basically this is like the index. So instead of giving a number to an index, we are using an object type, in this case a vector2 int. So what this means is we can use coordinates as the index to access the game object that we're going to be storing in this dictionary. We'll just call it clouds, and it's going to equal a new dictionary, and then you basically initialize them the same way that you do a regular list or queue. And then we're going to need a function for creating or converting a regular vector3 position, a global position, into something we can use with our dictionary. So let's just say private vector2 int cloud tile pos from v3. There's a nice mouthful of a name. And that's going to take in a vector3, which we'll just call pos. And then we're going to need another one, which is going to be a private int cloud tile chord from float, and that's going to take in a float value, and that's that. Now we'll start with this one because we're going to be this one we need in this one, so let's do this first. Random bracket there that we didn't need. So we start off float, and we're just going to call it a. It doesn't really matter what this one's called, and we're going to say value divided by, and then we need to cast it as a float, cloud text width, and this gets the position using cloud texture width as units. So what I mean by that is our cloud texture is 512 at the minute, so this gives us kind of a position, a coordinate, if 512 was 1 unit. So if it was 512, it would be 1. If it was 1024, it would be 2. If it was 4096 or whatever it is, it would be 4. And you get the idea. Then what we're going to do is say a minus equals mathf dot floor to int a. And then what that's doing is it's taking away any decimal places. So mathf.floor to int, if this returned a value of 2.467, this would equal 2. So saying a minus this would turn 2.467 into just 0.467. So that's what we're going to use it as. We're going to use the 0 to 1 value that we get from this to represent where we are in the actual cloud texture. And then finally we get int b equals mathf.floor to int, and then we need to cast this as a float. Cloud text width times a. So if a had ended up equaling 0.5 and the cloud text width is 512, then this will return 256, which is half of 512. So it gives us the position within the world relative to this tile map. But the good thing about this is it repeats, it wraps. So once you go past 512, it doesn't then start looking at 600 and something. It goes back to 0, and that's what we want. And then we're just going to return b. And then easily we can use this to get the value from here, which we're going to say vector2 int, new vector2 int, cloud tile chord from float, and we're going to pass in pos.x. There is no y because we're using a vector2 int, and if there was a y it would be 0, and then we want to set this to pos.z. That's that function done. So if we go to modify our create clouds function, and we're going to change this so that we have a vector3 position is going to equal a new vector3 x cloud height z, and we're going to change this to say clouds.add cloud tile pos from vector3, pass in the position, and then the game object, we're going to get our create our cloud tile thing the same way we've done in the other function. Create cloud mesh xz position, only it's not z, it's y. So what this is going to become now is, that's also y, this is a one-time function, and what this is going to do is it's going to run at the start and it's going to create all of our cloud objects. So I think 16 by 16, or is it 32 by 32? Yeah, 512 divided by 16. 32 by 32, which is like 10, that's 1024 cloud objects. So this is going to create all 1024 cloud objects and add them into this dictionary. And the idea is that once they're created, we don't need to create them anymore. We're just going to move them around. Like if you decide that you need your clouds to be further off into the distance than the 512 tile map allows, then you're going to have to mess with your code and change things. For this, I'm assuming that 512 is plenty for cloud view distance. So we're never going to need to duplicate any of these individual cloud tiles. We're always going to be able to just use the same ones, and when we need one at the other end, we can just take it from the far end rather than making another one. So if I run it now, it should work, but our clouds are going to be in the wrong place. Yeah, you see they're all off at 0, 0 because we're not offsetting them anymore, because we're going to be doing that using the player position. So to get out that player position, we need a reference to our world. So serialize field, private world, and again we're going to equal null, and again we will go drag that in before we forget, and then we're going to come down here and underneath create clouds, because you can put it wherever you want, this is just where I'm putting it, we're going to create a public void called update clouds, and we will copy this because I don't want to type it out again. Now, first thing we do is we get a vector3 position, and it's going to equal world.player. No, sorry, player is a transform, so world.player.position plus new vector3 x0z plus offset. And then we need to modify this position before we can use it, but to do that we're going to create a little function just to make things a little bit easier. So this is just going to be a private int, and we're going to call it round to cloud. And all this is going to do is, it's like float to int or whatever. It's going to take in a float value, and it's going to return an int value that is the cloud tile position that that value is in. So if there was a cloud at, well, there's a cloud at 16 by 16, like 16x, 16z. If we gave it 17, it would return 16. If we gave it 23, it would return 16. If we gave it 33, it would return 32, and so on. So it's just going to take in a float value, and we're just going to return mathf dot floater int value divided by cloud tile size, and then times cloud tile size. Oh, have I missed a bracket off here? Oh, no, I haven't missed one off. I've added one that I didn't need. So we're getting the value divided by cloud tile size, and then we're rounding it down so that we get rid of any decimals, and then we're timesing it by cloud tile size to get back to where we were, but minus the decimal points. So now we can use that value by saying position equals new vector3 round to cloud, and we're just going to pass in position.x. This time we need to use cloud height because everything is going to be set relative to the player, and if we don't set cloud height here, it's going to be adjusted by the way the player, by the position of the player, and obviously the position of the player goes up and down, and we don't want that. Don't miss off that bracket. And then once again round to cloud position.z. So that's going to, I keep doing this, it's a Y, not a Z. So that's going to adjust our position so that it locks on to an absolute cloud tile position rather than sort of shuffling around depending on where the player is. And then we're going to get a vector2 int cloud position, and that's going to equal cloud tile pos from v3, and we're just going to pass in our position. And then we're going to say cloud position dot transform dot position equals position. And remember, because we've created all the clouds already, and because we're not planning on using more than the initial 512 by 512 grid of clouds, we don't need to worry about whether this exists. We know it exists because we created it. So if I just quickly, just for our demonstration's sake, I put that there and then press play, the clouds are still going to be in the wrong place. Now the reason for that is because we're using the player as our marker, and that is the position the player was at the time the cloud's loaded, because the player's position doesn't get set immediately. The player's position, if I find our world script, gets set, where's generate world? Gets set here after we've generated our world. Well, the clouds are working much quicker than that. So if we go back into our clouds, delete that, we don't need that. We go into our world and we find some other references that it can group with. It looks fine. We're just going to create a public clouds, and then once again let's go and drag that in before we forget, so I don't get very confused by why we've got errors. And down here somewhere, there we go, clouds. So we just drag that clouds in, go back to our world script, and we want to find, where is it, player position there, just under here. We're going to say clouds dot update clouds. Now if we run it, we should find the clouds move to where the player is. There we go. However, that's not the end of it, because if I break my game again by grabbing the player and dragging him away, you can see the clouds still stay where they are. So we can easily fix that by just copying this line and putting it in, well, actually cutting this line, because we're not going to need it there, because as you can see, we immediately run check view distance after we've set the player's position, and all we're going to do is in check view distance, wherever I've put it, at the very top, we're going to call it there. So check view distance, if you remember, only runs once the player has moved from one chunk to another. So if the player sits still, this never gets called. So we call it once at the very start, and we're going to run this then, and then anytime the player moves from one chunk to another, we will call it again. So now, if I press play, you can see it's moved to where the player is, and if I grab hold of that player and drag him around, there we go, the clouds are moving with us. And eventually I'm going to run out of world here, but you get the idea. And that is an infinite and repeatable system. So those clouds are never gonna, unlike the world which has boundaries, the clouds are never going to run out or come up with an index out of range. So there is one last thing that we're going to do before I end this mammoth video, which hopefully will edit down into something a little more watchable than what I've recorded, is we're going to create a shader, because our clouds are solid and white, and obviously that's not how they look in Minecraft. So we're just going to create a little shader so we can make them transparent. So go into our scripts, create a shader, and we're going to use an unlit shader. It doesn't really matter because we're going to delete all of it, and we're going to call it cloud shader, and we'll open that up. This is a nice, this is nothing like all the other shaders I've done. This is a very short, brief thing. So shader, Minecraft, and we'll call it cloud shader. Oh, sorry, that should be in speech marks. And then we want our properties, and we've only got one property, and that is color. Which we'll just call color, of type color, and that's going to equal 1 1 1 1 by default. 1 1 1 1 1 is white and fully opaque. This last one, if you don't remember, is the alpha, the opacity. So this is your RGB, red, green, blue, and then how transparent it is. So by default, it's solid white and completely opaque. And then we need our subshader, and in here we want our tags, and our tags are Q equals, transparent, and ignore projector equals true, and render type equals transparent. And once again, that wants to be in speech marks, and we're going to say zwrite off. There's no semicolons here. Lighting off, because we don't want it to be affected by any of the Unity standard lighting because we're not using any of it. And we want fog, and for this one you have to put in curly brackets and say mode off. I have not done enough research into shaders to know what all of this means, why all of this works the way it does. For example, this next line, I'm not 100% sure it does, but I know it's necessary. So we're typing blend source alpha 1 minus source alpha. Okay, and now we can put our pass in, the pass I do understand. And in our pass, all we have to write this time, unlike the other shaders that we messed around with, is color, and then in square brackets, pass in that color value. And that is, I think, all of it. Let's clean that up a bit. We'll soon find out if we get any errors. Let's find our material, and clouds. Minecraft. Oh, I must have done something wrong because it's not letting me load it. We got, oh, we do have an error. Unexpected line 7. What have I done wrong on line 7? Oh, that should be tags, not tag. There we go. Okay, so if we go into our cloud shader, go into our Minecraft, we should, yep, there we go, clouds. And then I'll run it so we can see it in action live. We'll look up at our clouds. We should be able to alter the transparency. There we go. So make that as light or as dark as you want. I believe in Minecraft they sort of take on a bit of a blue tinge at night time, which is something we can now easily modify from within the script. But that's things like that I'll probably handle when I bring in time as an element. So like daytime, nighttime, that kind of thing. So for now, that's the end of this video. The only thing left to do is to thank my amazing Patreons, as always. And Professor DJ gets an extra special thanks for being an extra special supporter. But you are all very much appreciated, and I will be back very soon. I'm sorry this video was later than normal. My life is a bit of a hectic mess at the minute, including my house being a construction site. So yeah, I will get on it as soon as I can, and I'm thrilled to bits that you've all been so patient about this video. Thanks again, and I will see you next time. Bye-bye.